In the previous lecture, we have seen the phenomena of the induced voltage in a rotating loop. In this lecture, we will discuss the concept of induced torque in the rotating loop. Suppose a battery is now connected to the machine is shown in this figure. How much torque will produce in the loop when the switch is closed and a current is allowed to flow into it? Let at the start the switch is open. When we will close the switch, then how much torque will be produced in the loop? As we know, when a current carrying conductor is placed in a magnetic field, the conductor experiences a magnetic force. The direction of this force can be determined by Fleming's right-hand rule. According to Fleming's right-hand rule, middle finger will be placed in the direction of the magnetic field, index finger will point in the direction of the current, and thumb will show the direction of the force. So now let us find what is the force which is experienced here. As we know, the formula of the force is F is equal to I into L cross B. It means the length of the conductor and magnetic field should be perpendicular. And the formula of the torque is tau is equal to R cross F. It means the radius and force should be perpendicular as well. As you can see in this diagram, conductor AB getting current like this, that is outward, and conductor CD getting current like this, that is inward. So this is the North Pole and this is the South Pole. This is my conductor AB and this is my conductor CD. So this is the direction of the current is inward, as you can see in this diagram as well. The direction of the current across the conductor CD is inward, and the direction of the current across the conductor AB is outward. I have shown here as well. Cross means the direction of the current is inward and dot means the direction of the current is outward. What is the direction of the magnetic fields? Direction of the magnetic field is always like this. As we know, the direction of the magnetic field is from north to south. As you can see in this diagram, there are 4 segments in a loop. That is, segment number 1 is segment AB, segment BC, segment CD, and segment DE. Let's start from segment AB. As you can see in this figure, the direction of the current across the conductor AB is outward, and the direction of the magnetic field is towards right. That is segment AB. The direction of the magnetic field is towards right, and the direction of the current is to outward. or and the length and the angle between length and magnetic field is 90 degree. It means the condition of the force is fulfilled here. Therefore, FAB is equal to IL cross B is equal to ILB sine 90 is equal to ILB. As we know, tau AB is equal to R cross F is equal to RF sine 90 degree is equal to RF. Putting the value of F in this equation, we get tau AB is equal to RILB. This is the equation of torque across the conductor AB. So as you can see in the diagram, in segment AB, the direction of the current is outward and the direction of the magnetic field is toward right. So therefore, according to Fleming's right-hand rule, the direction of the force is upward because the direction of the magnetic field is toward right and the length of the direction of the current is outward. Thumb will show the direction of the force. So that's why the direction of the force is upward or counterclockwise. It means the direction of the current will upward. It means the direction of the torque will upward or counterclockwise. The next segment is segment BC. As you can see in this diagram, the segment BC and the direction of the magnetic field are parallel. It means the length of the conductor and the direction of the magnetic field both are parallel. It means the angle between length and magnetic field is 0 degree. Therefore, FBC is equal to IL cross B is equal to ILB sine 0 is equal to 0. As we know, tau BC is equal to or F is equal to 0. It means the torque across segment BC is 0. The third segment is segment CD. As you can see in this diagram, in segment CD, the direction of the current is inward and the direction of the magnetic field is toward right. That is, this is the direction of magnetic field and this is the direction of length, conductor. The angle between length and magnetic field is 90 degree. Therefore, FCD is equal to IL cross B is equal to ILB sine 90 is equal to ILB. As we know, tau CD is equal to RF. Putting the value of F in this equation, we get RILB. The last segment is segment DA. Again, as you can see in this diagram, the segment DA is parallel with magnetic field B. It means the angle between the length of the conductor DA and magnetic field B is 0 degree. Therefore, this is the magnetic field and this is the length of the conductor. Therefore, FDA is equal to I L cross B is equal to ILB sine 0 is equal to 0. As we know, tau dA is equal to RF. Putting the value of F in this equation, we get tau dA is equal to 0. So tau dA is equal to 0. It means the torque across segment DA is 0. The resulting total induced torque on the loop is given by tau total is equal to tau AB plus tau BC plus tau DA plus tau CD. Putting the value of tau AB, tau BC, tau DA and tau CD in this equation, we get RILB plus 0 plus RILB plus 0 is equal to 2 RILB. As we know, the shape of the rotor is in the form of cylinder. The area of the cylinder is A is equal to 2 pi R L. As you can see in this diagram, there are two number of poles. The first one is north pole and second one is south pole. The area of the single pole is A is equal to 2 pi R L divided by number of poles is equal to pi R L. That is A is equal to pi R L. The value of RL is equal to AP over 5. Putting the value of RL in the equation A, we get tau total is equal to 2I B into AP over pi is equal to 2 over pi I B into A. As we know, flux is equal to BA. Putting the value of BA is equal to flux in this equation, we get the final equation of the torque is equal to 2 over pi flux into I. As you can see in this equation, the total torque induced in a single loop depends on three factors. The first one is the constant, and second factor is the flux, and third factor is the current. That is, the relationship between torque induced and current is directly proportional, and the relationship between torque and flux is directly proportional as well. That's it for this week lecture. I will see you in the next lecture.